All right, good morning again, everyone. Today, I'm going to finish chapter 5. That's the plan, anyway. We're going to talk about how we generate random numbers from discrete distributions, arbitrary discrete distributions, and also we are going to see how we can generate random variables from arbitrary continuous distributions. We are going to see two methods from continuous distributions, the inverse transform method and the rejection sampling method. There are other methods as well, like importance sampling. We are not going to see them in this course. The two methods we are going to see for continuous distributions will be the inverse transform, taking the inverse of the cumulative distribution function, uh, which the cumulative distribution function's value has a really interesting property we haven't talked about before. The uniform, this cumulative distribution function's values, the y values, are actually uniformly distributed themselves. That's an interesting fact that we're going to see, which means that if we have a random number generator from uniform distribution, we can use the inverse of the CDF to get back to x values, which will then be distributed in the original distribution that we want to sample from. So that's the inverse transform method. We're going to see the details. But if taking the inverse of the cumulative distribution function sometimes may not be easy mathematically, and therefore there are other numerical methods, like this rejection sampling method is a very nice numerical method that approximates and samples from the desired distribution. So, and then we are going to see how we can use these generated random numbers in a Monte Carlo simulation with a specific size, and which will have some certain goal beforehand. For example, we will say that we want to estimate the probability within plus minus 0.01 within that distance. The probability, we want to get the actual probability within that distance with 95% probability, for example. We will have this thing. We will have some confidence in our Monte Carlo study, which is, we will say 95% probability we want this. And there's also the other thing is confidence and precision. How precise you want your estimation to be. And these two things will be used to estimate this, or to determine the size of the Monte Carlo study, how many samples, how long you should run your simulation to get to within this precision with that confidence. And we will refer to inequality by Chebyshev, which we skipped actually that part. It was in chapter 3.7. Section 3.7, we are going to just refer to that equation. We are not going to go into details, but we will use that to say, for example, if you want that precision with this confidence, you have to, for example, sample 40,000 times. You have to conduct an experiment in which you generate 40,000 random numbers. But these are really not that large numbers, 40,000. Which is manageable by computers we have these days. So we're just going to see how to estimate probabilities, how to estimate the mean and standard deviations by using Monte Carlo methods. These are the three things that we want to say. The remainder of this chapter, which we're not going to cover, talks about how you can estimate areas, or other integrals, other mathematical things. Monte Carlo methods are really useful. It's used to estimate certain things on also graphs. If you want to measure certain graph theoretic properties of a large graph, you can use Monte Carlo method. This is used a lot. I mean, if you look at research papers, when you become a graduate student, you will get to know this method in more detail if you take a graduate level statistical data analysis course. There's, for example, Markov chain Monte Carlo, or MCMC, which is a very famous method in high dimensional spaces too. So these Monte Carlo methods, but the main idea is you just try to compute something by generating random simulations that are taken from distributions of your random variables that are of interest. And I'm going to also take a look at an example. The assignment that we gave like 4 years ago, in the first time we offered this course in our department, I designed this assignment on Monte Carlo study, and I'm going to take a look at that homework and see the solution. We are going to take a look at that as well. Okay, so that's what we are going to do. Last time, if you remember, we have seen how we can use uniform random number generators, generator like this rand function in Octave Online. Uniform random number generators are available in many other languages too, Python, C. There should be some random function. So this random function, how does it give us these random numbers? If you look at those, they really look random. I mean, first of all, humans are not very good judges of whether they look random or not. If we were asked to generate these numbers manually by ourselves, we would probably not generate a uniform random distribution. We will have certain tendencies towards certain numbers. So our intuition may not be really random, especially when you look at the sequence. After, for example, you generate something with 0.36, I don't know the next number. Nobody's going to generate something that is with 0.35. These are too close to each other. We will try to distribute them in between 0 and 1 and get from here and there. But in randomness, these are really two independent numbers from each other. If the first one is 0.36, the second one can be 0.35 too. Okay, so you may you don't want to distribute them equally. So that's not really random. Humans manually cannot generate really uniform random distribution. So how are these numbers generated? There are different techniques. In the early 1950s, there will just like I think there's also in our appendix there's a table of random numbers. If you take a look at the appendix, continuous distribution tables. I think there were some random numbers maybe here. Random. Continuous families. Go to the next one. Yeah, uniform random numbers. Yeah, that was the first table. In distribution tables, as you can see, this is really interesting. What is this table for? This is not the CDF. In the other table, A2, A3, A4, we got the CDF function, right? So this is the CDF, cumulative distribution function for binomial, cumulative distribution function for other distributions. All right. So what is this first table for then? Look at this, just a bunch of random numbers. These random numbers, that people use these tables in 1950s. It only contains like 400 of them, 400 random numbers. If you're going to conduct a simulation of size 400, you can use this table. So if you use this table starting from the first number, always 0.95, 83, 79. So what will happen is that your simulation is not going to be random. It's going to be basically deterministic. Every time starting with the same random numbers, going over all the random numbers. One thing you could do is, in order to make this a little bit random, you can just close your eyes and put your hand on one of those numbers and start from there, and then do the simulation. This is called like seeding a random number. We just seed our starting point, and which may be random. Just closing your eyes and pointing your finger at one of those may be something that is random. And this is a table of random numbers, and I don't think anybody uses such tables anymore. The truly random thing is, for example, you may have some physical, you may have your random numbers tied to something physical that are independent from each other. One thing that is these days, many of those languages, programming languages like C, Python, they provide actually pseudo-random number generators. They generate random numbers from a mathematical function whose period is very long, which means that it doesn't get to the first number that is generated for after maybe 1 billion numbers. And the series in that mathematical series looks really like random. And maybe each of those numbers within certain range are equally likely. So that's by some mathematical function you walk through in this series of numbers. And every time you start with the first number in that series, again, you're going to get the same numbers. Therefore, what you would do is you would again use a different seed, just like pointing your finger arbitrarily at one of those numbers. You can start in that mathematical series with some truly random position. And that truly random position people use most of the time is the system time in milliseconds, for example. If you use every time you run your program, the start of the program in milliseconds is something random. You can use it to point your finger at that mathematical series in the pseudo-random number generator, and every time you run your program, it will look like it's really random. So if that milliseconds time is really something random, why don't we use it instead of the random number generator? The thing is, the first time function, the first time you call it, it will be random because the time it spans between two running your program consecutively the second time. You may be doing something, you may be editing your code, you may close. Let me try to demonstrate to you. So I'm going to just write this in C. Okay, let's call this random.c. I think this random is included in stdlib. Let me also print out some numbers. Include stdlib. So I'm going to write a C program here, and I'm going to use the time function, which is in time.h. So what I'm going to do is generate some random numbers and see how they are random. So the srand function in C is the function to seed the random number. So there's this time function that you can call. Time gives you the milliseconds that have passed since 1970 something, if I'm not mistaken. So it gives it's counting the time since some reference time, and it gives you that in milliseconds. So this large integer number that is returned by time can be used as a seed. And every time I run my program, this srand time null is going to give me some milliseconds, which looks like it will really be like some random physical thing. You start the starting of your program. So we can generate a number of for example, let's generate 100 numbers, and let's print them out. So the way the rand function works is that it generates integers. So we can call this function like this. Let's see what kind of integers it's going to generate, and finish our program gracefully. So let's run this random.c. Okay, so when you run it, it generates you a bunch of numbers which all look like positive integers, maybe between 0 and some large number. So what you could do is, so these are all integers, not floating point numbers, but we could do something like this. If we want to generate them as uniform random numbers with precision 6 points after the digital, the decimal point, 6 digits after the decimal point. What we could do is we could just generate, we could take the mode of this number, 1 million. So which will turn our numbers to numbers between 0 and 9999. And we can then divide this by 1 million. But I don't want this to be an integer division, so I make it a floating point division. So let's print out this number as a floating point number. So this is a double. If you want it float, you write it like this, but it doesn't matter actually. Okay, so this becomes a floating point number. Let's see what will happen if I do this. Let me. Oh, there's this I. Why did I put this I? Yeah, it should be. This is 100,000, 1 million. Mod 1 million. So when you run it, as you can see now, we have ourselves some random numbers. They look like uniform random between 0 and 1. Since I generated, they were between 0 and 1 million actually, the integers. If you divide them 1 million, you get yourself numbers between 0 and 1, uniform random numbers nicely. So this is how you can use if your random number generator gives you big integers between 0 and some maximum integer, you can do this. By the way, again, I hid myself behind this window. Now, yeah. All right, so this is, now what I was saying was, if this time is really like a nice function, instead of this, why don't I directly use time? Let's try that. Instead of calling the random function, why don't I use time? And the answer is actually not that difficult to figure out. Although the first call to time will be random because some random time passes between I edit this function. I mean, the number of milliseconds that pass after I edit this one and compile and rerun it is really like random. But the time that passes between each iteration of this for loop is not that random, right? I mean, this time, every time you call this time, the number of milliseconds that passes will be one iteration. So they will just be increasing numbers. They will not be random actually. So that's why we don't use time. I mean, the time functions that you use here, they will be dependent on each other, and it will depend on how fast your CPU is, the number of milliseconds. So therefore they will not be random. So we only use this time function to just point our finger at some position, and then so if you compile it, you'll see what kind of random numbers we generate. Look at this; they're actually all the same because the number of milliseconds that pass the program was so fast. The entire program finished maybe in less than a millisecond. That's why we got all the same thing. Okay, it didn't look random. So what you can say is, okay, let's have some delay. We can sleep, or we can have some for loop, which goes from 2 billion or some large number, and maybe do some dummy thing here. Let's have some float a. Okay, so I just put there to have some delay to see what will happen. Oh, I think my loop condition here, j is equal to 0, it was too large. So the delay was too big. So let's reduce the delay. No, it did only one time. So why? Oh, because, yeah, it was only a single statement. I forgot to put these block and curly braces. Yeah. So now when you say random, oh, it's still like that. So it was not a big delay, actually. This was... Yeah, you see how it I mean, do they look random to you? They're just incrementing every couple of times. They don't look random, as you can see. Okay, just putting a delay, the delay will be constant. So we cannot use the time function as a random number generated. But the first time, so here, let's erase these things and get back to our program. So when you run this function, as you can see, the first random number you generate is 0 0.04 and then 0 0.19, 0 0.03. You run it again, it starts with something else, 0 0.616146, and you run it again. So every time I look at these random numbers, the number of milliseconds that pass when I'm talking here, it's really like a random event. So therefore you get yourself a non-deterministic random looking program. All right. So anyway, our goal was, I spent too much time on this thing, but hopefully it will give you some ideas about how you can use. You're not only tied to Octave Online, you can write your own programs in any language you like, and this by the random function provided by them. So what we did was we used first this. For example, if we have some Bernoulli variable with some p, 0.8. And what we did was, by saying rand less than p, okay, we were able to generate random numbers from a Bernoulli distribution. Sometimes it becomes 1, sometimes it becomes 0, and the number of zeros will be roughly equal to 20% of your samples, and 80% of the samples will be 1. Okay, so we're just sampling. Sometimes we get 0, sometimes we get 1, depending on then the number of times we get 1, the random number will be less than 0.8. 80% of the time, 0 with 0.8 probability. So this is how we get ourselves a Bernoulli random variable. So first, until the break, I'm going to show you some other random number generations, discrete distributions, how we can use the same idea to even generate random numbers from some more complicated distributions. We'll see all discrete distributions, and then we will see another problem where we want to generate random numbers from an arbitrary discrete distribution. You'll understand what I mean in a couple of minutes. So I spent a lot of time actually on this slide when I was talking about how we generate random numbers. So there are pseudo-random number generators, which are long sequences of random looking numbers with some mathematical function, which with no surprise that they use prime numbers. Okay, prime numbers help us get these random looking things. And the start location in this long sequence becomes our seed, and as we have seen in this example, we have used the system time in that example. And many systems also provide standard uniform random number generators. If you don't have that, you can just use the mode function, divide the resulting integer with another floating point number to get a uniform random number. Now, the first part of this book, 5.2, let's get to this one. It's all about, 5.2 is all about how we generate random numbers from any distribution using just the uniform random variables. So 5.2 is all about that. And then after we have those random numbers generated for our distribution that are in question, we generate a lot of them, and then we conduct a Monte Carlo simulation. And by using these, we are going to see how we can estimate probabilities and means and standard deviations. So this is what we did for Bernoulli last time. We have the Bernoulli has only one parameter, p, probability of success. We generate a single uniform random number. If that uniform random number is less than p, we generate a 1. If it's greater than or equal to p, we generate 0. Again, since uniform is continuous, whether this equality is going to be here or here is just a convention, because the point probabilities of uniform of continuous distributions are 0. So it will not matter if you take the integral from 0 to 8. If you include 0.8 or not, the integral will still be 0.8. So this is the probability of success. So we were able to generate a Bernoulli variable. So let's come to the next one. How do you generate a binomial variable? What's a binomial variable? Remember again, it's the sum of n independent Bernoulli variables. So we may just do that. Generate n random numbers. And so Octave Online has nice operators that work on matrices, just like MATLAB. MATLAB is for matrix library. It can, the single operators we have, this less than or summation or things like, they work on entire matrices or arrays directly. So you don't need to write loops. The iteration is inherent in it's implicit in those operators that you use. So let's take a look at this example and let's try to code it in MATLAB or Octave Online. Let's do that. So what was our binomial variable has two parameters this time. The parameters are 20. What is so it becomes an integer, it's discrete, the number of successes in 20 tries, where the success of the probability of success of each try is 0.68. So here, let's do that. So n is equal to 20, p is equal to 0.68. So first I generate my random numbers. So I generate random numbers. Was it? Oh, I didn't say rand. Okay, so I generated random numbers, 20 of them, which are these. So let me see the syntax here. So U is now a single one-dimensional array which contains a bunch of uniform random numbers. Now, my Bernoulli variable will just be the sum of the cases where this U is less than P, right? U is less than P, it's going to be 1. It's a success, so we count it. So this U is less than P. This less than operator is going to be applied on all members of the U array one by one. And it will, actually you can do it like this. If you just write U less than P, you'll see that it turned these uniform random numbers into a bunch of ones and zeros. It's still, the result of this operation is still a one-dimensional array. And you say sum, it just sums the entire contents of the array. So it counts basically the number of successes. So if you do that, 14. So we generated the value of 14 to generate a binomial variable. Do that again. And you say sum. So it's still 14. Is it working? It should be working, right? So do that again. So is it, yeah. Again, another random number, 12. So it was working. Now it's 12. So 14, 14, 12. So if you want to generate a bunch of binomial, so this is to generate a single binomial random number. If you put it inside a loop, if you want to generate, for example, a number of, a number of binomial variables, you just need to do this again and again, okay, for each of those binomial variables. So we just count. Geometric, again, we can just count. We start with, we iterate and count the number of generated random variables until first success. Let's take a look at this example. The probability of success is 0.16. And we start our variable at x is equal to 1. If the random variable is greater, while the random number is greater than p, this is a case of not success, if you remember, or not success contained inequality as well. You can say while the random variable is greater than or equal to p. Again, it doesn't matter whether you put equality or not, because this rand is a continuous variable. So while this part, if you want to insert a comment here, while not successful, you increase it again and generate another number. So if we don't enter this while loop, if the first time was a success, if the random the number that is generated is less than p, for example, we generated 0.14. which means that it's successful. It will be successful in 0.16 of the time. And if the generated random number was 0. Here, the loop condition is run. If 0.14 was generated, we would exit this loop because it's less than that, and then you'll just report 1. As long as it's unsuccessful, we keep incrementing that, and in the first success, in the first time when rand is less than or equal to p, we just quit this while loop, and that's our first success, and our count is going to say our count value will be our geometric random variable. So let's try that here. Again in Octave Online. So let's call this variable g. Use a different one. For example, if the success probability was 0.11, okay, and g, I initialize it to 1, and here is what I'm going to write. While random is greater than p, g is equal to g plus 1. Do I do it later? G is equal to with a semicolon at the end. Okay, now when I hit enter, it's going to run this entire loop, and I say, and I look at g, the value of g. So I didn't see so what was wrong here? So I think it's still in the loop. How do I end this loop in Octave Online? So I have to write and, sorry. And so it wasn't still in the loop. So since I said g here inside the loop, it also for every iteration it's displayed g. So let me run it again. So while this g is equal to g plus 1 and end. Okay, now the whole loop has run. When I say g, I can say it's 16 now. Okay. If you want to generate another random variable with the same parameters, you run your loop again and look at what g is. It's again says 16. So let's do it again. Oh, by the way, we didn't initialize g, right? Oh, that may be a problem. Yeah, I should choose g is equal to 1. So I should have initialized g. So yeah, g is always being incrementing here. So I'm getting some cumulative things. So that was, so you should just try this again from beginning by reinitializing g to 1 and run your entire loop and generating this right and comparing to this one. Okay, I think g was initialized somehow. It was because it was 17. It was still a small number. I'm not sure, but yeah, you get the idea. You have to run this loop to generate a single geometric random variable. It's just counting how many trials are needed until first success. And negative binomial is just a summation of geometric variables, which means that how many trials you need, not until first success, but to get k successes. Now we have another variable k, which means that you have to put this in a loop that goes k times. So we have another loop here while I is less than k. So we generate a geometric variable. We add this geometric variable to total number of trials to our sum. X at the end becomes our negative binomial variable. So each of the time we run this inside loop, we generate a geometric random variable, and that's an independent geometric random variable. We add its value to our sum, and we do this exactly k times to get the number of trials needed for k successes. All right. So now here is the question. How efficient is generating these binomial, geometric, or negative binomial random numbers? Bernoulli is O1, right? We generate in O1 time the Bernoulli variable. What about binomial? What did we do to get binomial? It was The number of successes and trials. What is the complexity, time complexity of a binomial? Can you write it in the chat box? Let me ask this question again. Let's get back to this. So Bernoulli, I can generate a Bernoulli variable. Now we are talking about time complexities, how efficient these random number generators are. You know, one time we generate a Bernoulli variable. For the others, we had some loops that run in certain times. So they don't look like O1. So what are their complexities? In binomial, we have the two parameters, n and p, okay, for a binomial. So what was the time complexity to generate the binomial variable? I just said a single statement, right? Is it also O1? Yeah, you did not fall into this trap. It's ON. Yeah, you're right. It was a single line of statement. It was sum u great less than u less than p, but it was running on the entire array contents. So I told you that there's an implicit iteration over this. So it's exactly ON. So we had to generate n uniform random numbers and sum them up. So first generating n of them takes n time. It's another on time to sum them up, but it's on at the end. Okay, O2n is on. Now, what about, it gets a little bit more complicated when you start talking about the other things. What about a geometric? Geometric is also just one parameter, p. It doesn't have n here. So I don't think we can just have a function that says on. But how long does it take? The geometric random variable was in a loop. Sometimes we may have to generate more random numbers, sometimes less. Can you write its time complexity with respect to p? What was the, how long the while loop is going to run? Probably it's going to be, by the way, if it never finds it, it may be actually infinite. The worst case, if you have a very small p, but we may talk about the expected values. The expected value, what is the expected value of a geometric variable? The number of trials we have. I think that expected value can be used. The expected number of trials until first success will be also the expected number of times our loop runs, right? If just think about p is equal to 0.1. What is the expected number of trials until first success? 10. So our loop also is expected to run 10 times. But in the worst case, since the range of a geometric random variable is between 1 and infinity, your loop may, with some probability, with some non-zero probability, you may run your loop a very long time. So its worst case may be infinite. That's very bad, right? I mean, if worst case complexity infinite, best case complexity or 1, and on the average, its average time complexity, I think it's going to be 1 over p, right? So which contains p in it. So depending on if your probability p is, for example, if it was 1, it will always be 1, right? If your success probability is 1.0, it means that you're going to for sure get your success in your first try. So it will just take one iteration. So if your p is small, you're going to tend to increase the while loop is going to run more. So we can say the expected value of this geometric variable is the average running time of our geometric to generate a single geometric random variable, and this will be not surprisingly in negative binomial, which is the summation of k geometric variables. We can just say it will be k divided by p, because the expected value, we will run the loop k times each of those independent geometric variables. We will run the inside loop 1 over p times on the average. Again, its expected value will be k over p. And depending on what p is, for example, if you have a very small probability, p is equal to 0.001, and k is maybe, for example, 1000. What is the number of trials until getting 1000 successes when p is equal to this small probability? So you will have to run in order to generate a single geometric variable, you will be spending like 1 million, 1000 divided by 1000th number, it gives you 1 million. So to generate a single geometric variable, you may have to generate 1 million uniform random numbers. These are inefficient ways actually. So there's also a more efficient way to do this. Because even though the p is small, we can also use, these are all discrete distributions. If you look at this, let me get a new slide. If you look at this discrete distribution and look at the CDF, the CDF itself is between 0 and 1, right? Here, the first thing is the probability. Let's talk about a geometric variable. A geometric variable is going to, the probability to get one, in one trial, the probability to get a success. For example, if p is equal to 0.1, okay, the probability to get your success in your first trial is going to be small. So 1, 2, 3, go. It goes like this. I'm going to write 10 somewhere here. But what I want to show you here is that since these are, I'm showing you the, let's take a look at the PDF first. So it's going to be small like this, and then I think it's going to get a bit larger, and it's going to get its largest value somewhere here, and it's going to decay very soon. And for certain numbers, for example, you may, even for 0.01, p is equal to 0.01, the values that you have here, maybe after a certain point it's going to get very small. Or if you look at the CDF, certain parts of this distribution may be negligibly small. So what I'm trying to say is that if, although it goes all the way to infinity and your worst case complexity is infinity, what you can do is you may have a way to find if this was the CDF. You may partition your CDF into regions. For example, what is the probability to get, this CDF value here shows what is the probability to get 3 or less trials. And this is CDF of 2, so the difference will give you the PMF in discrete distribution. So what I'm trying to say is that we may generate a single uniform number and try to see where this uniform number is going to fall in this CDF domain, which the values of 1 to there, it may be infinite, but the CDF values will be 0 and 1. So by just looking at where this single uniform number falls in, we can actually figure out, based on where it falls in. If it falls in here, for example, we are going to generate a 3. If it falls in here, we are going to generate a 2. So, and we can apply this general technique to any arbitrary discrete distribution as well, but we may also use this technique to make these binomial, geometric, or negative binomial random number more efficient to generate. Instead of trying to simulate the trials, the Bernoulli trials one by one, we can actually directly refer to the CDF of that and partition that space into regions. And the general case is going to be like this. Imagine my random number takes values between 1 and 10, okay? And this probability range is divided into, for example, the probability that it's going to get the value of 1 is this. The probability that it's going to get 2 is this. 3 is this. So these pieces can be figured out from the CDF directly. So I can have some values here. Maybe the probability to get a 10 is this. Look at this. So this is the entire probability region from 0.0 to 1.0. So the CDF starts at 0, goes all the way to 1. This is how your CDF behaves. Now, in a discrete distribution, if these are all the values your random number can get, instead of generating these 10 uniform random numbers, I generate a single uniform random number and figure out where this uniform number falls inside this partition of the CDF. If it's here, for example, I'm going to generate a 9. If it falls here, I'm going to generate a 2. And if you look at the probability to get a 2 will be the same as this area and this uniform number, whatever this interval is. The probability that the uniform number is going to fall in this region is going to be equal to u is in that bin. Okay, so here, this is what we can do to generate these random numbers. And for a random variable which gets infinitely many values, it may not be at first seem possible to partition this space between 0 and 1 to infinitely many bins. Okay, but some of these bins will be very small, and for after certain values we may consider they're all together they follow. For example, if u falls between after this, for example, if u is larger than 0.9999, then you may generate always, for example, 15 or 16, whatever that large number is, or some large number. So that it may be divided into infinitely many partitions, but after those points, those partitions will be very small. So if you look at the CDF of geometric or CDF of negative binomial, you see that after certain values we get very close to, so the CDF is going to reach to very close to 1.0 after certain numbers. So that's what we're going to, so that's some generic technique. Instead of simulating Bernoulli variables one by one, we will be using, actually I was trying to draw that figure on GIMP, but I already have that in the slide. So here, if you look at this from 0 to 1, and you consider this as your CDF, that increases from 0 to 1 by 1. So the probability to get a value of x2 or less will be equal to p0 plus p1 plus p2, right? So this is the cumulative distribution. The probability to get a value xn or less, if all xn is your largest value in the your random variable can take, the probability to get xn or less will be equal to 1.0. And in this, if you have such a thing, if your variable gets n different values, well, you can actually generate a random variable in on time, again in linear time. First, what we will do is this: we will generate a single uniform random number, and then figure out where it falls in this interval. So how do you figure out where a single random number falls in a bunch of n intervals? You start from your first interval, look at interval endpoints, and if your u is smaller than endpoint, it must be in this interval. So you start at this p0. If it's less than p0, you generate x0. If not, you look at if it's less than p0 plus p1. Then, which is the end of this interval. And if it's so, you generate an x1. If not, look at this. If not, look at this. Again, in ON time, in worst case ON time, you would be able to generate uniform random number from this arbitrary distribution. So let me ask you a very interesting question. This was an interview question at Google's job interview. Can you generate a random number from this arbitrary discrete distribution not in ON time, but can you do it in O1 time? And you're allowed to pre-process this discrete distribution in ON time. So what I'm saying is that you're first going to do something with this, given such an arbitrary discrete distribution with P0, P1, P2, Pm probabilities, n of them. If you're going to generate just one number, you're bound to spend ON time, that's for sure, okay? But imagine you're going to be generating millions of billions of random numbers from the same distribution. So what you want to do is, maybe you want to spend n log n time or even n squared time, doesn't matter. You just have a way to pre-process this discrete distribution to turn into some data structure. And with that data structure, every time you want to sample a random number from this distribution, your goal is to do it in O1 time. Okay, so can you generate random numbers from an arbitrary distribution in O1 time was that interview question, and the answer I think is actually on the next slide. At least the name of the method is on the next slide, but I think it's a good time to have a break. You may think about the solution during the break if you want to, and after the 10-minute break I will continue with this arbitrary, and we're going to start talking about continuous distributions. Okay, let me stop recording now. See you all in 10:42.